Lastly, I want to talk about dosing, and I want to introduce you to a maintenance dose and a loading dose. So we're going to start with the more commonly used, the maintenance dose, which refers to the dose required to maintain steady state. So let's use again a bucket analogy. So let's suppose we're going to give a drug to a patient, so a certain dose. And so what's going to happen in the beginning, we're going to fill the bucket. We're going to fill it, and eventually we're going to reach the concentration that we want to give this patient, and that's the plasma concentration at steady state. But we need to consider that elimination is also going to kick in, so we can think about it like this bucket has a hole and it pours out here again. So we want to find a dose that maintains steady state. So that means the rate of elimination needs to equal what I put in the drug dose. So they need to be equal. So how can I calculate the maintenance dose? So the maintenance dose is a concentration at steady state times the clearance, because I have to consider that I'm losing stuff, divided by the bioavailability. So we should not forget that whatever we put in here, not everything may reach the plasma. So we can think about it like putting a filter above and say, well, that's our bioavailability. Not everything will make it. But at steady state, the rate of elimination needs to equal the drug dose that we put in. And I also want to mention, how long will it take to reach steady state? Well, it's going to take 4 or 5 half-lives to reach steady state. What about if you don't have the time to wait till you fill the bucket and then reach steady state and have the dose in which the rate of elimination equals what you put into the bucket? Well, then there you have another possibility. That's a loading dose. And the loading dose you're going to get by multiplying the plasma concentration at steady state times the volume of distribution, where does the drug go, divided again by the bioavailability. Why does the volume of distribution play here an important role? Well, if you have a very large volume of distribution, what do you think your plasma concentration is going to be? I hope you're going to say you're going to have a low plasma concentration because the drug is everywhere. It's not just in the plasma, so it's low. So that means your loading dose will most likely be very high in order to get to steady state very quickly. You can also do the opposite. If you say you have a very low volume of distribution, well, then the concentration in the plasma is going to be high and you need a lower loading dose to reach it. Importantly, just you need to consider, you need to calculate in the volume of distribution because that matters. But getting back to, well, if you don't have the time to wait to steady state, that's when we use a loading dose. When would that be? Well, in a critically ill patient. Critically ill patient. So let's suppose you have someone with meningitis and you don't want to wait with an antibiotic 4 to 5 half-lives to reach steady state. You're going to basically fill the bucket without having a hole. So you're just going to fill the bucket with your volume of distribution to reach steady state. And again, you need to calculate in the bioavailability. So you're going to have some sort of filter here. And that's a drug dose. That's your loading dose that you're going to get to immediately get to the plasma concentration you want to have. So you're not going to wait 4 to 5 half-lives till you reach steady state and then equal the rate of elimination. You're just going to fill the bucket immediately with a high loading dose.